Okay, Jane, here's the discussion for the problem number 5 on the cone. The formula for the volume of a cone is 1/3 pi r squared h. And the key to problems like this is realizing that you've got similar triangles to deal with. At any given point in time, the height of the water level is given by the letter h, and that's what's changing. And this radius of the water level is also changing. And what we're looking for is a relationship between r and h. And you can see the big red triangle is a right triangle with legs of 5 and 10, and the little blue triangle has legs r and h, and those two triangles have to be similar. They're similar actually because of angle. You've got a right angle in both triangles, and this is a common angle. And you could even prove corresponding angles for these two angles right here. But anyway, so the proportion that you can set up is that r is to h as 5 is to 10. And we want to solve for r so that we can replace r in all these formulas in terms of h, because that's what we're given. We're given the value for h, and we're given dh dt. We're not given anything about the size of r or the rate of change of the radius. So I have circled in green the fact that r is always equal to h divided by 2. R is always half of h, whatever the water level is. So for part A, we're supposed to find the volume of the water in the container when h equals 5. That's the area of this shaded region right here when h has a value of 5 centimeters. So all I did is substitute into the formula 1/3 pi r squared. Well, when r is 5, I'm sorry, yeah, when r is 5, I'm sorry, when h is 5, r will be half of 5, or 5 halves squared. So 1/3 pi r squared h. So this is h, and this is half of h, or the radius squared. And that results in 125 pi over 12 cubic centimeters. So there's your answer to part A. For part B, what we want to do is take the formula for the volume of a cone. We want to get rid of the r, because we don't know dr dt, and we could find a value for r itself, but it's easier just to replace everything, all the r's, in terms of h. So 1/3 pi radius squared is equal to h over 2 squared times h. So the formula for the volume of the water that's in the cone is 1/12 pi h cubed. And you could put 5 right in here and get 125 pi over 12, the same thing we got in part A. So part B, that first row, is a formula for the volume of the water depending strictly on h. So now we're going to take the derivative with respect to t, implicitly differentiating with respect to t. dv dt equals, look over here all the way to the right, 3 times a 12th is a 4th. We're using the power rule. 1/12 pi is just a constant. So 3 times 1/12 pi is 1/4 pi. Reduce the exponent by 1. Use the chain rule. Derivative of h with respect to t is dh dt. So there's the formula for the rate of change of the volume with respect to time in terms of h. And now I substitute what I know. 1/4 pi. We want to find dv dt when h is 5. So there's 5 squared. and the rate of change of h with respect to t was given as -0.3 centimeters per hour. I didn't put the units on here, but if you put the units on all these variables, you'd see you do end up with cubic centimeters per hour, because this would be centimeters per hour here, and here you'd have centimeters squared, so you get cubic centimeters per hour. And I reduced this to -15 pi over 8. For part C, show that the rate of change of the volume in the container due to evaporation is directly proportional to the exposed surface area. What does that mean? Well, when two quantities are directly proportional, that means that you can set up an equation that looks something like this: y equals kx, where k is a constant of proportionality. So as x goes up, y goes up. Directly proportional. So I want to translate that information into an equation. So let me go to red. The rate of change of the volume, that's this, is, that's the equal sign, directly proportional to the exposed surface area of the water. dV dt, we've already seen, is this from part A, or from part B, right here. 1/4 pi h squared dh dt. K is the proportion of constant of proportionality. Now, how do I find the surface area? Well, that's just the area of a circle. So the surface area is equal to pi r squared. But we've seen that r is h over 2. So I can write this as pi h over 2, the quantity squared, which is pi h squared over 4. And so that these two right here cancel out, and that allows you to find that the constant of proportionality is really the rate of change of h with respect to t. So that proportion of constant of proportionality depends on how fast the rate of the water, or the height of the water, is changing. Okay, I hope you understood all that. We can clarify next time if you have any questions. I'll end the video.